Welcome back. This session focuses on the mathematical transition from simple to multiple linear regression. We are moving from a 2D plane to an n-dimensional feature space. Using our previous dataset, we've added a new feature, number of persons visited. We will now demonstrate how the model adapts to this increased dimensionality to minimize loss across multiple variables. In this expanded dataset, we had two input features, the bill amount and the number of persons. Our target variable remains the tip amount. This configuration allows us to represent the data within a three-dimensional coordinate system. The objective of the multiple linear regression model is to determine the optimal plane that best fits these data points while minimizing the overall loss function. The objective of our model is to define an optimal plane, which serves as the predictive surface for estimating the tip amount. With the tip amount represented on the z-axis, the linear equation for this plane is formulated as z hat equals w1 x1 plus w2 x2 plus w0. Building on the foundations covered previously, we evaluate the performance of this prediction plane using the mean squared error MSE loss function, which is defined as MSE equals 1 over n times the sum from I equals 1 to n of z hat I minus z I squared. Let us examine our final loss function. We have three unknown parameters to determine, the weights 1 and w2 and the bias term w0. The objective of our model is expressed through this optimization formula. Arg min w1, w2, w0. MSE. This is interpreted as identifying the specific values for w1, w2 and w0 that result in the absolute minimum possible loss. Before we explore the mathematical process of how machines actually learn these weights, if you find this content valuable, please consider sharing it and subscribing to our channel. To reinforce your learning with interactive quizzes and hands-on projects, be sure to visit our learning platform at www.wisdomers.in. We now move to the implementation of gradient descent for our multivariable model. Since we are optimizing for three unknown parameters, w1, w2, and the bias term, w0, we must apply three simultaneous update rules. As you observe these equations, I invite you to visualize the loss surface. While we previously worked with a 3D landscape, our current model exists in a four-dimensional space. To converge at the global minimum, we compute the partial derivative of the loss function with respect to w1 formulated as partial L by partial w1, and apply the same logic to w2 and w0. To initiate the optimization, we begin by assigning random values to our parameters w1, w2 and w0. We then iteratively apply the gradient descent algorithm until the model converges to the global minimum. This process allows us to identify the optimal weights that minimize our loss. Crucially, this mathematical framework scales to any number of dimensions. If your dataset contains n features, the model constructs an n-dimensional hyperplane. While we are currently focused on linear equations, keep in mind that these same principles are used to map complex, non-linear surfaces in neural networks. We invite you to share your insights and learning experience in the comments below. Your feedback is valuable to us. We wish you a highly productive and insightful learning journey.